Hello, everyone. How's the Josh today? Are we feeling high energy? I really hope so, because welcome to this explainer. Today, we are diving into the absolutely fascinating mechanics of chemical reactions and equations. We're going to explore the fundamental principles of how matter interacts, transforms, and literally reorganizes itself on a microscopic level. It's an incredible journey into the actual building blocks of our universe. So let's get focused, grab a notebook if you need one, and unlock the secrets of chemistry together.
Okay, let's dive into this. What happens when milk is left out at room temperature during a scorching hot summer day? Or, when an iron nail is just left exposed to a humid atmosphere in the pouring rain? We have all seen the aftermath, right? The milk goes terribly sour and clumps up into this gross texture, and the iron nail gets completely covered in that flaky reddish-brown rust. But why does this actually happen? Well, in both of these highly relatable everyday phenomena, the actual nature and identity of the initial substance have fundamentally changed at the molecular level. The atoms themselves have completely rearranged. They've undergone a true chemical reaction.
Here is our roadmap for today. First, change is all around us. Second, the language of chemistry. Third, balancing the chemical scales. Fourth, the four reaction types. Fifth, heat, speed, and redox. And finally, number 6, chemistry in everyday life. We are going to demystify every single reaction, equation, and balancing trick along the way.
Let's kick things off with Section 1. Change is all around us, understanding the basics.
Basically, the universe is constantly transforming, and this change happens in two main ways, physical and chemical. Now, a physical change is when the state changes, but the core properties remain exactly the same. Think of melting ice. It goes from a solid to a liquid, sure, but molecularly, it is still just H2O. It's just water. Or consider tearing a piece of paper. It's smaller, but it's still paper. But a chemical change, that is entirely different because the actual composition changes. Burning that paper creates ash and gases like carbon dioxide, completely new substances. Or think about baking a cake. You mix flour, eggs, and sugar, but once it comes out of that oven, you cannot unbake it, right? A really brilliant everyday example is a burning candle. The wax melting down the side, that's simply a physical change. But the wick actually burning and combining with oxygen to create light, heat, and smoke, that is a definitive chemical change because a brand new substance is being formed right before your eyes.
Moving right along to Section 2, the language of chemistry, spotting reactions. You don't need a high-powered microscope to see chemistry happening right in front of you. You just need to look for specific physical clues. Now, what's really interesting about this list is that you only need to spot 1 or 2 of these to catch chemistry in action. Ask yourself, is there a sudden change in state? Did the color completely shift, maybe from a clear liquid to a deep dark blue? Are there bubbles? Bubbles indicate the evolution of a gas. Just think of that intense fizzing and bubbling when you drop an antacid tablet into a glass of water. Boom! That's a gas evolving right there. Did the test tube suddenly get hot to the touch, or surprisingly cold? Or did a solid, cloudy precipitate suddenly form out of 2 clear liquids? See these signs, and you've spotted a reaction.
So when chemists observe those reactions in the lab, they need an efficient way to write them down. Writing out magnesium ribbon burns in the presence of oxygen to get converted into magnesium oxide takes way too long. Who has the time? Enter the chemical equation. It is a precise, shorthand way of representing a chemical reaction using symbols and formulas. Think of it exactly like this. Just as we use emojis to text our friends faster, conveying a whole complex mood in just one tiny symbol, chemists use these specific equations to write out complex molecular reactions incredibly efficiently. Let's break down the actual anatomy of an equation, so we're all on the same page. On the left-hand side, or LHS, we have the reactants. These are basically your starting ingredients. In our magnesium example, it's magnesium, written as Mg, and oxygen, written as O2. The arrow right there in the middle is incredibly important. It literally translates to yields or produces. Then, on the right-hand side, or RHS, we have the products. This is the brand new substance that was successfully formed. Here, it is magnesium oxide, or MgO. The reactants on the left completely transform into the new product on the right. Simple enough, right?
So the crucial point is coming up right here in Section 3, balancing the chemical scales, the golden rule.
This brings us to the absolute foundational rule of chemistry. You probably remember this from Class 9, the law of conservation of mass. Mass can neither be created nor destroyed in a chemical reaction. This isn't a suggestion, it's an unbending rule of the universe. It means the total mass of the elements present in the products has to be exactly equal to the total mass of the elements present in the reactants. Why is it so strict? Well, atoms don't just magically pop in and out of existence. Every single atom of carbon, oxygen, or iron that goes into a reaction must be absolutely accounted for when the reaction is finished. Simply put, if you start with 10 atoms on the left side, you absolutely, unequivocally, must end up with exactly 10 atoms on the right side.
Let's actually do this. Let's walk step by step through balancing iron reacting with water. We start with Fe plus H2O yields Fe3O4 plus H2. Right now, it's a mess. It's unbalanced. We have 1 iron atom on the left, but 3 on the right. No way! That breaks the rule. So, step 1, draw invisible boxes around your formulas. You cannot change anything inside those boxes. You can't mess with the molecular structure itself, only the numbers outside them. Step 2, list out your atom counts for the left and right sides. Step 3, equalize the biggest molecule first. Here, that is the oxygen in Fe3O4. We have 4 oxygens on the right, so we're going to place a big 4 in front of the H2O on the left. Step 4, now we balance the rest. That 4 we just added gave us 8 hydrogens on the left, so we have to put a 4 in front of the H2 on the right to match. Finally, we put a 3 in front of the Fe on the left to perfectly match the 3 irons on the right. And boom, the math perfectly aligns. 3 Fe plus 4 H2O yields Fe3O4 plus 4 H2. Beautifully balanced.
All right, shifting gears to Section 4, the 4 reaction types, chemistry's playbook. Let's look at the different ways these atoms can swap partners. The first type is the combination reaction. This is exactly what it sounds like, when 2 or more reactants combine to form a single new product. And this brilliantly illustrates how 2 completely distinct things can fuse into one. For example, when calcium oxide, which is quicklime, reacts vigorously with water, they combine together perfectly to form a single product, calcium hydroxide, or slaked lime. 2 ingredients in, 1 result out. Another fantastic, everyday example is simply hydrogen gas combining with oxygen gas. When they react together, they form a single product that literally covers most of our planet, water, H2O. Next up is the exact opposite of that, the decomposition reaction. Here, a single reactant breaks down to give 2 or more simpler products. Imagine you have this massive, complex structure made out of Lego blocks. A decomposition reaction is like tearing apart that complex Lego structure into its individual, simpler blocks. Often, this requires a push, external energy in the form of heat, light, or electricity to force that single substance to break apart. A really concrete chemical example is what happens when you heat limestone, which is calcium carbonate. Applying intense heat forces it to break down and decompose into calcium oxide and carbon dioxide gas.
Our third type is the displacement reaction. Guys, this is where the molecular drama actually happens. It occurs when a more reactive element displaces, or effectively kicks out, another less reactive element from its compound. This whole dynamic is governed by something called the reactivity series. A classic textbook example is dipping an iron nail into a blue copper sulfate solution. Iron is higher up on the reactivity series. It's a tougher, more reactive metal than copper. So the iron boldly kicks the copper right out of the solution and takes its place. It forms iron sulfate, and the pure copper is just left behind, kicked to the curb. Similarly, if you drop a piece of zinc into that exact same copper sulfate, the zinc will also easily displace the copper because it is much more reactive.
And then, naturally, we have the double displacement reaction. This isn't just one element kicking another out. It is a mutual exchange of ions between 2 entirely different compounds. It's a swap. If we mix sodium sulfate with barium chloride, the barium and the sodium literally swap their chemical partners. The fascinating result here is that barium sulfate is formed. In a real-world lab setting, this looks absolutely incredible. You mix 2 perfectly clear liquids together, and suddenly, boom, the entire mixture turns a milky, cloudy white. That white solid? That's the barium sulfate. It is an insoluble solid, meaning it simply won't dissolve, so it slowly sinks to the bottom of the test tube. We call that sinking solid a precipitate.
Let's move on to Section 5, heat, speed, and redox, the hidden forces. We're going to look at the invisible energy that governs all this.
So, let's talk about the energy behind these changes. Reactions either aggressively release energy or they consume it. Exothermic reactions are those where heat is given out along with the products. Burning absolutely anything like coal, wood, or natural gas is highly exothermic. It releases a massive amount of heat into the environment. Endothermic reactions are the exact opposite.
Energy must be absorbed from the surroundings for the reaction to even happen. We mentioned decomposition reactions requiring heat earlier, remember? That makes them endothermic. Another amazing endothermic reaction is photosynthesis, where plants absorb massive amounts of energy from sunlight to convert water and carbon dioxide into glucose. Or, if you want a fun lab trick, if you dissolve ammonium chloride and water, the test tube will actually feel freezing cold in your hand because it is rapidly absorbing the heat directly from your skin.
Now, what about the speed of a reaction? That introduces us to a truly fascinating concept, the catalyst. A catalyst is a substance that speeds up or slows down a reaction without being consumed itself. One of our sources shares a brilliant, kind of funny anecdote about this. Imagine a guy named Mintulel. Mintulel goes up to two of his friends, whispers nasty rumors in both of their ears, and causes a massive fight between them. But Mintulel himself? He doesn't throw a single punch. He just walks away completely unharmed. That is a real-world catalyst. It jumps right into the chemical mix, dramatically speeds up the reaction, but emerges at the very end perfectly intact and completely unconsumed.
Let's move to and see how this builds into our next major concept, redox. Redox is a clever little portmanteau of reduction and oxidation. Oxidation is when a substance gains oxygen. Reduction is when a substance loses oxygen. The absolutely crucial thing to understand here is the paired nature of these events. Oxidation and reduction always, without fail, happen together in a pair. It's a cosmic transaction. Think about it. If someone is gaining an oxygen atom, they had to steal it from somewhere else, right? Which means another substance in that exact same reaction is definitely losing it.
Let's map this out clearly with a classic redox example so you can see exactly who is stealing and who is losing. Copper oxide plus hydrogen yields copper plus water. Look at what is happening to the hydrogen on the left side of the equation. It starts out entirely alone, right? But on the right side, it has successfully gained an oxygen atom to become water. Therefore, the hydrogen was oxidized. But where on earth did it get that oxygen? It aggressively stole it from the copper oxide. The copper oxide loses its oxygen to just become plain copper. Therefore, the copper oxide was reduced. One steals, one loses. That perfect balanced transaction is the heart of redox.
Which brings us to our final section, Section 6, Chemistry in Everyday Life, Why It Matters. Let's zoom back out to the macro level.
Oxidation isn't just a textbook concept trapped in a laboratory. It is constantly happening all around us, often with huge real-world consequences. When metals are systematically attacked by moisture and acids in the air, they undergo oxidation. This is called corrosion, and it's the exact reason our bikes form that flaky, reddish-brown rust we talked about earlier. On a larger scale, corrosion causes catastrophic damage to car bodies, bridges, and iron railings, literally costing global industries billions upon billions of dollars every single year in maintenance and replacement. But oxidation also relentlessly attacks our food. When the fats and oils in our snacks are oxidized over time, the process is called rancidity. It chemically ruins the smell and the taste of the food, making it go horribly bad. So the exact same chemical process that can slowly destroy a massive steel bridge is also responsible for ruining your favorite potato chips. It's wild.
Which brings us to a final thought. To actively prevent that rancidity, food manufacturers actually flush bags of chips with an inactive gas, usually nitrogen, to block out the oxygen completely. So the next time you open a puffy, nitrogen-flushed bag of chips, ask yourself, what invisible chemical reactions are you preventing today? And beyond that bag of chips, think about what other invisible reactions are silently governing our biology, powering the stars above us, or driving the technology we use every single day. Chemistry isn't just rigid equations on a page, it is the dynamic, ever-changing story of the universe itself. Thank you so much for joining me on this explainer, and keep exploring.